Welcome to our field trip series at the American Museum of Natural History, and today's topic, mapping the universe. I'm Carter Emmart. I'm the director for Astrovisualization at the museum, and I'm here with my colleague and friend, astronomer, astrophysicist Jackie Faherty. Jackie?
Hi, everybody. I'm Jackie Faherty. As Carter says, I'm an astrophysicist at the museum, and Carter and I are going to be co-touring this map of the universe with you, which we're very excited to do. And before we get started, I wanted to acknowledge today, yesterday, many people probably saw that Governor Cuomo signed an executive order that New York State now recognizes today as a holiday. This is Juneteenth. And I would be amiss if I didn't recognize this right now as a moment that we're all reflecting. And in my own field, in physics and astronomy, I think it's very important to hear that Black STEM students are woefully underrepresented. We have less than 2% of PhD grad students that are Black. And what I can say today is a day to reflect on that. Anybody watching that's Black, that is getting excited by this, please enter the STEM fields. We definitely need you. And more than that, I want to encourage everyone that's watching to look at the hashtag #AmplifyBlackSTEM. It's a beautiful hashtag, which is telling the stories and showing the voices of many Black students, Black STEM researchers throughout the world. So Carter, with that, I think you're moving us around the universe right now. One thing I have to make sure I say, I'm going to be monitoring the chat and I'm going to be looking to see your questions live. I'll be gathering them. There are 3 other scientists that are in the chat, Mordecai McLough, Brian Abbott, and Marina Gemma. All 3 will be answering your questions live. I will be taking them, and as you ask them, say your name and where you're from, and I can give you a shout out. So with that, I think we're about ready to get started, Carter.
Great. So today, thank you, Jackie. And we're going to be looking today at the universe and how we map it, obviously. But the universe is interesting. It's an ancient word. It's a very ancient word. It sort of means one verse. It means basically all of space and time and their contents. So we're talking about planets, stars, galaxies, really all of energy and matter in all forms. That is the universe. But it really starts with looking at the sky. And at looking at the sky, we're going to be using our software Open Space. If you're interested in obtaining it and using it yourself, you can do that. It's freely available, NASA funded. And in our chat, our team will be able to steer you in the right direction to that. We're looking at the night sky, actually, from a location. I'm just going to sort of run time a little bit here. And we've noticed that the sky rotates around us. The sun rises and sets, and here we see a beautiful sunrise. And the stars that we see, I'll bring up the constellations. We'll talk about what those are and how basically these are groupings of stars that have been noticed in the night sky. And I show you now the Big Dipper here, rising in the dawn, and the front of the Dipper is part of the Big Bear, Ursa Major, and it points up to a Little Dipper constellation up there. There's that's sort of, I'll put it center screen for a second, and the sky seems to rotate around this star. And so with the constellations, I'll point out, because things rotated around it, I'm having to fly this myself today. I'm going to just bring up a way in which we grid the sky based on that rotation around the Big Dipper. And now the sun has come up. We are showing the stars. Even when the sun comes up, the stars seem to go away because the sun is so bright. But our location here is in our beautiful national park, the Grand Tetons in Wyoming.
And
so
Carter,
I'm going to just pause time for a second. Yes, Jackie.
Well, I wanted to give folks a chance. I know we have a lot of students on here. I'm seeing a lot of kids in the chat already. And you can envision for yourself the dark skies that you've seen. And as you're looking at this sky that we have up for you here, I want you to try and guess which one of these stars, based on just what you're looking at, which one of these stars might be the closest one to you. How would you tell that? So look at the sky here, and think about it too from when you've seen it in the nighttime. And maybe when you go outside tonight, you can do this as well. But how would you pick? Would you go with the brightest star? Would you go with the one that has a color that it might be closest? Or maybe it would be something about where it is in the sky. All of those were things that astronomers thought about as maybe a clue to what might be the closest star. And so Carter's now pulled us away from the Earth, where we're getting this phenomenal perspective that certainly Carter has not had this viewpoint ever. And we're moving away. And as we do, you're going to start to see the Earth come away and the stars really come out in a different way. Carter, you might want to say something about what the Earth looks like here too, because we're about to get a really gorgeous view of the Earth.
What we're doing is we're looking here at the Earth and the thinness of the atmosphere. This is a map that's been brought to us by satellite imagery, and it's been pieced together with the company Esri that fortunately shares this freely with us. It's similar as a product to, you may have heard of Google Earth or played with that. But also now fading up is another map, which we see the clouds fading in, and that's thanks to NASA. NASA actually supports multiple satellites observing the Earth, and so it gains us a view of the Earth sort of every day. And this is yesterday, in fact, on the Earth. Why not today? Well, today is still being mapped. So I'm going to pull this out just a little farther, and so that we can look back at our beautiful planet Earth. North America has just come into view.
And Carter, so we're getting questions. I saw one from Anna and one from Alexander, 4th grade and maybe 3rd grade in here, as to just say a little bit more about what constellations are. And so we're moving around here, and should say that constellations, there's 88 of them that are official designated constellations by the International Astronomical Union. And they are basically the boundaries of the sky. And what's cool about them is that they are kind of like stick figures or drawings that people saw, shapes that they saw, but also boundaries. And they were the stories that people told as well. Carter's got the Earth here, but just behind it, there's the scorpion that just kind of came down very low. What you're seeing is in the representation here with the lines connecting the bright stars you would see in the sky and how people saw stories played out. What's important, though, for you to realize is that these constellations are two-dimensional interpretations of what the sky looks like. It's like looking at wallpaper, right, Carter? You love to describe it as wallpaper.
Well, we've been looking at the sky for a long time. Our ancients looked at the sky and made maps of the sky. And we know from them that because we inherited those maps, that the sky hasn't changed very much. And today, in the program today, we really want to sort of emphasize that the mapping of the sky as one thing. But through that, we understood the nature of the stars. And then through that, we understood the nature of the universe, really. So yes, the wallpaper of the night sky. How far away is the night sky? It's beyond our reach. We gave it the name, the celestial realm, because we really don't understand. We didn't understand how far away it was. What was the sun? What were the stars? What was the Earth?
And from
basic
that
questions.
Perspective, Carter, you've got us kind of moving around, and we're going to talk about distances in this presentation, because distances is basically one of the key components to making a map, especially one in 3 dimensions. And what you're bringing into view now is one of the most critical first distances you can have in astronomy before you launch off among the stars. And so that is, Carter's bringing into view, that bright light is our sun there. And so you see the Earth, and the sun is there in your outer space sky here. And it was very, very important to understand how far away that sun was before we could launch off and then move amongst the stars. So astronomers were able to do this once they realized the Earth goes around the sun, and we could use events. The one event was used, it was the transit of Venus, and it was used to try and get an idea of how far away the sun was.
I'm going to bring up the orbits of these are lines that have suddenly come on screen, but if I pull away far enough, we can actually see there's a little orbit around the Earth. That's the moon, And then these colorful lines will, if I move far enough away, we can see these are the trails of our orbiting around, like a racetrack. We're all going around the sun.
Yep, we just had a question come up by Leo as to where is the moon, and we just passed it, Leo. It was in orbit around the Earth, which right in there, Carter's just brought up the labels. The Earth is the blue line, the third rock from the sun, and the moon is going around the Earth in that perspective. And so you can see the Earth goes around the sun, and it's roughly 93 million miles between the sun and the Earth. So we will talk in distances basically up to this point. We're not going to say much more in miles because the distances are about to get really, really large. So we're going to switch to talking about light time. Right, Carter? This is our...
Yes, and also it's another thing to note is that the sun, as we show it here in open space, kind of looks like a really bright star. But we weren't sure of that when the ancients weren't sure of that as they began to map the sky. So that the first thing was, what were the stars and how was the sun different, I guess.
And so when we're in this perspective here, where we can see the Earth going around the sun, key first distance is we know that the sun is 93 million miles away. And we're going to move away just a little bit. And I think before we show off too much, Carter, we should say these are the bright stars of the sky. What's really important to know as well is that this is not everything at all. There is so much to the universe and there's so much to the nighttime sky that you unfortunately can't actually see. We're going to take you to a couple of those places today. We thought we might wow you a little bit here to show you stars that you don't necessarily get to see at all. Well, you definitely don't with your eye. Your eye can see just about to Saturn. I saw a question about that coming up about what's the faintest planet you could see. Takes you to Saturn, and then you can't see the others, Uranus, Neptune, and that other one out there beyond.
Again, if I turn the labels on, that's Uranus out there. And if I'll pull out a little farther, Jackie, and so that we can see all of that. And we'll see Jupiter come in. It's the fifth planet, and then the sixth.
And so once you're out there at Uranus, you can't actually see that with your eye. It's too faint. These stars here are much farther. You can see them because they've got nuclear engines. They got a big engine at their core. And so they can shine very bright from very far distances. We're going to pull away, and then let's give a wow moment, Carter, where we show them stars they can't see, but we can map, and we will be taking you beyond their mapping.
Sure. And Jackie, I've got a favorite data set of yours. I know it's a subject of your research, the Gaia data set here.
Carter's going to bring them up slowly, so don't be scared. There are a lot of stars out there. And Carter has brought this up. We've made it quite bright. This is unreasonably bright, meaning we have increased how bright these stars are. Again, your eye can't see these stars. So let's stop scaring them a little, Carter. It's a lot of stars. But those, just to give you a little teaser, there is so much out there. And there's so much out there for us to explore and map. And we're going to talk to you about some of that mapping now. So as we've been moving around here, you haven't seen the stars change. We're too close to the sun and the Earth. So let's move away a bit. And we just got a question from Roy Soto about, do stars orbit the sun? And a great question, Roy. The planets orbit our sun. Other stars might orbit each other, but we currently in our solar system have just one star that we know about. Everything else is actually orbiting the center of the Milky Way galaxy, which Carter has brought up, which is streaming across your view right here.
So I'm going to use the sun, which is the center of the target, of course, of all these orbits as we all go around. I'm going to align our target, if you will. In fact, I might actually be able to use my cursor to bring it over, and I point out the sun in the middle here. But there's a fairly bright star next to the sun right now, and some of you may have heard of it. It's called Alpha Centauri, and it's the nearest star to us.
And I should note, we got a question from Alexander, who's in 3rd grade. How long would it take to get to the sun? And I think we didn't emphasize this enough, but The distance between the Earth and the sun was 93 million miles. But miles, we're going to start talking about distances that are just too large. We don't talk in miles anymore. It is actually, we measure everything by light, how long it takes light to get from place to place. Light is the speed limit of the universe, and it moves at roughly 186,000 miles a second. And so it would take roughly 8 minutes to get to the sun from the Earth if you could travel as fast as light can. So keep that number in mind, because Carter's going to take us out to some light distances, right, Carter?
I'll also point out that Neptune is the blue orbit that we see beyond Uranus. It's the last orbit that we see. And that light takes about 4 hours to go from the sun. It takes 8 minutes to get to the Earth, but it takes 4 hours to get to Neptune. And then the distance to the stars is something that was only begun to be figured out, Jackie, about 150 some odd years ago, right? Or
yeah.
1836, right?
Roughly, yeah.
Okay.
So let's see. Carter's got this great viewpoint coming out of kind of moving away from our solar system, and you can still see these constellations, which again, for those that maybe have joined late, the constellations are kind of like how we connected the stars to make shapes or stories. And we still have those stories in the nighttime sky now that we tell. And he's moved us around so you can see to the left of the sun here, which is now becoming just this glowing ball that contains the whole solar system, is a cross, what looks to be a cross.
I'll use the sun as a pointer. If I bring it over there in the middle, we can see the Southern Cross, which we don't see from here. We have to go down to the Southern Hemisphere.
Right. That is a very beautiful constellation to look for in the southern sky. But key to this is, now look around. For any of you that were trying to guess before what the closest star was to you, we're going to show it to you. And as Carter moves back and forth, look for the object that appears to, as Carter really eloquently put, is moving away from the wallpaper and is shifting.
And Jackie, I just thought I might encourage some of you that may have noticed this, but if you hold your finger up to the end of your nose and blink your eyes back and forth, you'll see that your finger seems to move. So it's a perspective effect. And if you move your hand farther out, you'll see that your finger doesn't move as far. And so this is the technique, right, Jackie, that we use to figure out distance just from the Earth's orbit around the sun. Is that correct?
This is the exact kind of thing that we do in astronomy, similar to how you have a distance between your two eyes, which allows you to see things from a perspective where you can measure depth. What we do, and I'm going to do a throwback to that number we just said before, that 93 million miles between the Earth and the sun. If you looked at the stars on one side of it and then the other, you would actually see the closest ones jump back and forth, just like Carter is showing right now as we move left and right. And that first star that's moving across, moving away from the wallpaper, that is Alpha Centauri, which is one of 3 stars in a triple system. And he's
turning back a little bit so that we can see the full word, Alpha Centauri.
Alpha Centauri. So it's in the constellation, the Centaur, and the Greek letter designation of Alpha means that it's the brightest star in that constellation. So it gets Alpha Centauri. So it is a very bright star. But here's a cool thing. It's actually not the closest star. There's another star in that triple system that's too faint for your eye. So you couldn't actually see the closest star. It was almost a trick question I was asking you when I said, what star do you think is the closest? Alpha Centauri is a part of that triple system, but the star Proxima Centauri in it, which is just too faint. It's too low of a temperature for you to see. And now Carter's giving us a little tour. These are your friends, ladies and gentlemen, and little ones that are in here. Look around at these stars. Have a look at these names. These are your closest stellar neighbors. You've got Sirius there. Carter's brought up Sirius, Procyon, Vega, a beautiful blue star that is in the constellation Lyra, which is a part of a triangle a triangular formation we see in the nighttime sky. We call it the summer triangle.
I'll line up with Lyra, and I'll just come in a little closer, Jackie, so that we can kind of see that. I pulled out a little too far, so everything starts to distort. But now we can see Lyra the way we see it in the summer sky.
And Bud Jackson just asked so we can remind Bud and everybody else that the words that you're seeing are the labels of the stars. This is the most common name that we have for these stars that astronomers would call these objects when they're talking about them, and that we catalog them as.
And I'll say one other thing, Jackie, is just that the larger the label, the closer they are. Vega is only 20 light years away. That's a tremendously far distance to compared to maybe the grocery store, but these that's just sort of a typical interstellar distance, I guess, for our part of the galaxy.
And so, Carter, why don't we fly out a little bit more and give folks an idea of how far away we're going to get. So we're going to move in a way that is not possible for humanity to move at a speed like this. We're moving amongst the stars at more than light speeds in order to get away from the sun. And now look at this. Look at all those constellation lines. So those were those two-dimensional representations of those great stories of the nighttime sky. Those stars that we saw as 2D projections, they actually, for the most part, don't have anything to do with each other. They're just stars that are in the same vicinity of the sky, but at very different distances from each other.
You might wonder how far away we are now. We thought, since we're talking about light travel time and the sun's 8 minutes away and the nearest star, Jackie, as you mentioned, is 4 light years away, at this point, we want something to show basically that maybe that we as humans have generated that might be out there amongst the stars. Well, we have created a form of light called radio, and since the Earth began generating strong enough radio signals, has reached out about 80 light years. So really around the birth time of television and an early radar that was used in World War II, mid-century essentially, but or just before that.
I think we can turn the constellation lines and labels off here too, Carter. As another important, for those that are just joining us too, welcome to our YouTube stream. We are talking about mapping the universe from close to the solar system, and we're going to take you out to the galaxies shortly. But Carter right now has shown the radiosphere, a distance of, what did we say, Carter, 80 light years?
Yes, it's 80 light years in radius, and so it's keyed to about 1939, 1940. Yeah. Mm-hmm.
And so he still has labels of star names on here, but what we wanted to show you as we're talking about mapping is that we've moved beyond our solar system. Anytime we talk about mapping, we'd really like to bring up other solar systems. And I've seen we've gotten a couple of questions in the chat about other solar systems. So Carter, why don't we bring up for everybody the markers around stars that have exoplanets. This is exciting to see. Every one of the stars now that has one of these blue circles around it is one that astronomers have looked at and found at least one, but maybe more, other planets. So they've had big planets, small planets, Earth-sized planets, Jupiter-sized planets, and much bigger than Jupiter-sized planets. So these circled stars all have had a detection of a planet. And you can see some of them are within that 80-ish light year sphere there, where the radio signal from Earth has washed over. And so it's a really cool thought process to go down, that these are the solar systems that could have had a signal from Earth. Now, it would have been a very washed off signal, but they're within the radiosphere from Earth, which we always think of as a beautiful thing to consider.
And to give you a sense of how new this information is, if you're 25 years old, you were a baby when the first one was discovered in 1995. You can see a whole bunch going off in one direction. That's from the Kepler mission. But Jackie, I thought I would also, let me just come back to a star cluster that's fairly popular, because we see it in the winter constellation of Taurus. And
Yeah, and
um,
we're getting, just to throw in some questions from
mhm.
the chat. Fernando is asking about new constellations or more constellations. There are 88 constellations in the sky, and that's pretty much set. Although those are just the official International Astronomical Union constellations. You can look up in the nighttime sky and see whatever pattern you would like as well. It's your nighttime sky, and you could write a story and create your own constellation. And I would encourage any kids to do that. It's a really fun thing to go outside and connect stars and see shapes.
Jackie, one of the things you said to me yesterday, which I really thought was great, was that while the constellations are associations that we see of different stars of different brightness and color and so forth from Earth, that just has to do with our perspective, but that these clusters actually do physically exist together, and this is, I guess, arguably one of the closest clusters to us. The Hyades cluster, or the face of Taurus the bull, the star Ain is one of the eyes of the bull.
Yep, and you can see this cluster, which, just in case anybody's curious, so these are all stars. We call them clusters because they've clustered together, these stars. They were probably born together and are evolving together. So they're growing up together. So it's like identifying the family members that are near us. So as soon as we can measure distances to stars, which we've shown you, now we're in 3 dimensions and we're measuring distances to stars, you can actually identify the families, who's moving with who, who's hanging out with who in here. And Carter pointed out Hyades. Hyades is a family that's about 650 million years old. So that might sound old to you, but that's actually pretty young in astronomy, 650 million years. And so those stars that we just flew by are all moving together. And they're not the only ones. We can show you more than that.
So I'm going to bring up a mapping of them, and there are a lot of them. So we see, once again, the Hyades cluster right here, but then there are others that we see all around us, and they tend to cluster around the Milky Way band. Is that right?
That's right. And we're getting a reminder from the chat to give you guys a reminder that that blue sphere there is the radiosphere, and it marks about an 80 light year distance away from the solar system. So it's giving you a distance map so that you can see where we are. And Carter's brought up, so every one of these green dots here, what you're seeing is the location of one of those moving families of stars. So each one is a tiny map of its own of stars. Sometimes they have hundreds of stars, sometimes thousands of stars that we've identified that all move together and are evolving together. And they're different ages. Most of them, these clusters here, they're what we would call young. But again, when I say young, they're under 1 billion years old. So you can say that that sounds old, but we're talking astronomy here, and 1 billion years is still pretty good, still kicking it. That's a very youthful age, I think, Carter.
Jackie, why are they clustered, and do they start together when they're born? Do they leave the cluster kind of like a nest of birds? What's the story with them?
Yeah, and we're getting questions exactly about that in the chat too. So how do these family members get started? Well, they get started from clouds of hydrogen that come together, and you get the hydrogen collapses basically, and you get it to fragment into pieces, which are stars. And so Carter can bring up as well, on top of this, these are clusters that are definitely together, but now these blue and purple dots that you're seeing are the location of the youngest associations that we have of stars. So they get born in these giant factories, star formation factories, and they have a cloud, it fragments, it makes a lot of stars, and they stick together at the very beginning, and then they all move around the galaxy together. And as they move around the galaxy together, then they can interact with other stars or with other big molecular clouds, and they start to break up, and you kind of lose your families a little bit. But most of them stay close to where they're born, which is why Carter's got us lined up here. See how we're basically lined up here with that beautiful band of the Milky Way that you could
just move around to it. Sorry, I want to get into where we actually really see it nicely there, and Okay, Jackie. Yep.
Nice. You're getting us towards more of the center of the galaxy where it gets nice and bright and
Mhm.
beautiful. And so you can see that these locations here of your youngest stars, they stay close here. And I've seen questions in the chat here about what exactly is in the Milky Way. Well, this is where a lot of your stars are. This is like the downtown. This is the area where everything happens. It's the Manhattan of the galaxy of the galaxy. It is the galaxy. When you're
Not
looking
where
along,
we are, in the center of the galaxy. We live in the burbs.
the sun is in the suburbs. I would say the sun's like off in Long Island in an area. Not so crazy underdense, but it's definitely less dense. And so Carter's brought us out here. Those locations there are the locations of the star forming regions, and they're different colors because they map the spiral arms of the galaxy. So we think that we've never gotten this view. This is really important. This is not a picture, right, Carter? You can speak to this beautiful image that we have up here.
So that's right. What we have in open space is actually a simulation from our colleagues at the National Observatory in Japan. And we started working with them for our space show called Dark Universe. And so working together with our visualizers and their scientists, we were able to construct this map of the Milky Way galaxy. It has stars and it also has gas clouds in it. And but it's not just a picture. The research was actually charting where the gas clouds are that are somewhat associated to like these OB associations. And then a model is run of the dynamics or how the galaxy actually works. And so together that forms the picture that we see. If I pull out even farther, we actually augment that a little bit with a galaxy that's very similar to the Milky Way. It's called NGC 1232, and so that we see that. But Jackie, I know that we were talking about stars before, and of course the importance of the stars to sort of even understand the galaxy. And I know you're Gaia stars, so maybe we show them here. We showed them in close, but let me show them again.
So to give people the highlight here is that mapping the stars where they are, like how far away they are, it's really hard to do it. You need very high precision, like really good cameras in order to be able to do it. It's one of the oldest traditions in astronomy to measure distances, and Carter's brightening up the premier mapping mission. It's from the European Space Agency. It's called Gaia. And it has been mapping from about 1 million miles away from Earth, orbiting Earth at 1 million miles away. It's been mapping almost 2 billion stars. And what Carter is showing you there is about 8 million of those stars. He's brightened them up. So it's a very large luminosity. And you can see that we have redefined astronomy with this mission, yet we still haven't mapped a significant portion of the galaxy. And it's both intimidating in the number that it has, but it's also it's not the whole galaxy. So we're working on more stars.
It's about 1%. Well, it's measuring about 1 billion stars, and that's about 1% of the whole galaxy. We could see that it was on one side of the galaxy because it's where we see them close to us, I guess. But also by understanding, I guess, the property of stars, Jackie, I'm going to just swing around. We see a couple neighbors coming into, they're just as sort of green disks here, but these are our neighbors of the Magellanic Clouds.
Yep, and before we get to those, I just want to answer a question from the chat from Andrea Avila Silva, which is, what is the light at the middle of the Milky Way there? And I just let you know, that's the center of the Milky Way. That is the core, that's the height of the action for our galaxy. So it's the densest part, which is why it's so bright, because there's so many stars in that particular area of the galaxy. And now Carter's moving away. We had a question from 7-year-old Colin about how many galaxies do we know of. We're about to take you there, Colin. Carter brought up SMC and LMC. So he's labeled everything now that you see beyond the Milky Way there is a galaxy. So we're no longer talking just stars in our own Milky Way. We are beyond that. And the LMC and the SMC are very close. Go ahead, Carter.
And we've given a nice little name because there's no place like home, of course. Although we share our home, in the Milky Way galaxy, is what we call it, in honor of the Milky Way band that we see in the sky and the ancients saw in the sky. But it's home to several 100 billion stars and maybe even 1 trillion planets at the rate we're finding them now. Yeah, so that all of these, every point you're going to see something like IC10 up there. That's another galaxy. It's staggering how many galaxies we have.
Yeah, and important to this is that if you want to start measuring distances and do your three-dimensional map out here, you can't use the same process that we were just talking about, where you look on one side of the Earth and the other side of the Earth and you see the thing jump. Instead, you have to go to a couple of things, one of which is that those galaxies that were close by, the SMC, or the Small Magellanic Cloud, there was a woman named Henrietta Leavitt, and back 100 years ago, what she did was that she found a kind of star that was in the SMC, the Small Magellanic Cloud, and she noticed that it had a very, very tight relationship between its change and how its brightness would change, because stars sometimes get bright and dim, and how bright it was. It's called the period luminosity relationship, or Leavitt's law, after Henrietta Leavitt. So you can use that to create what we'll call standard candles, which are objects that you could identify in other galaxies like the ones we're flying around, and then know exactly how bright they should be. And you can do the same thing with supernova, when a supernova goes off and a giant star explodes. And Carter, you've just taken us into a very crowded area of galaxies.
Yes, we're about 60 million light years.
I think we might have
just
muted
a moment.
Carter.
Sorry, I muted my microphone because we got a call coming in. Yeah, this is the Virgo cluster. We're about 60 million light years away, but they're so-called Virgo because it lines up with the constellation Virgo way, way, way back down to the tiny, tiny little Earth when we look up. This is a map by our friend and colleague Brent Tully from the University of Hawaii, who put together this map that surrounds us out to several 100 million light years, if you can believe that. And I'll brighten them up, Jackie, and then we'll pull out even farther. And I think that's about all the time we've got.
Yeah, I think we should also remind people of how far away we are as we're moving away, because we have gone to distances that are unfathomable to say in miles for sure. You have to talk in light years away. And we are in the millions of light years away at this point, once we get outside of this little clump of galaxies here. So reminding you, every dot here contains billions, hundreds of billions of stars. You are looking at what we call the large scale structure of the galactic neighborhood around the Milky Way and beyond. So this is the large scale structure of the universe that we're starting to unveil to you. It is just like we saw those stars that'll clump, like the Hyades we reminded you of early. Galaxies clump as well. So we're moving away, and Carter's now bringing on another sample of galaxies. Carter, this is the Sloan Digital Sky Survey, right?
Sloan Digital Sky Survey, and you may notice that here you see that clumping gets even more sort of emphasized in a broader view. So this is like a larger sample. This should extend, and it does extend completely around us, but it seems to have almost like butterfly wings. That shape is because of what we call an observational bias. It's just where we look. It doesn't mean that there are no galaxies out in the dark area. It's an area where we've yet to map.
We don't have much more time, but I think we should get some questions answered here too. Leo asked, "What's the mass of the Milky Way?" And that is a really large number, as you have about 100 billion stars, 100 to 200, maybe 300 billion stars. So in that is a very large mass to give you. But think of it as maybe the sun, bigger and smaller together, 100 to 300 billion of those. So you can't put it on a scale, right, Carter?
No, but you estimate, and we can estimate based on that the mass. If you add up all the stars, add the gas, and so forth. But It leads to something called dark matter, where there's more matter there seems to be there than we actually see. That's a reason to study astronomy. It's fascinating. It's always interesting. So.
Another great question from Jessica Wilk-Stanley, and I think Jessica is a student in our Master's in Teaching program at the museum. Jessica's asking, if we lived in the center of the galaxy, would we even have a nighttime? Would we even have a night sky with so many stars nearby? And I love this question. It's one that I think about a lot, of what the nighttime sky looks like from different areas of the galaxy. And it all depends on what's around you. It is certainly a different construct when you're at the center of the galaxy with so many stars. And we can almost simulate some of that within open space, right, Carter, by flying to different places?
Yes. And in this case, I mean, we could fly in and it would start to look similar to what we showed you when we faded up the Gaia. So I think I'll not go there. I'll just come back to Earth because it's probably easiest for me to do right now. But anyway.
Yeah, and as we come back in, I'll answer
staggeringly large.
One other question, which I love, from Alan White: has the closest star to the sun always been 4 light years away? Were we closer to another star in the past? And the answer is absolutely yes. We've been closer to other stars, and we will be closer to other stars very soon. It is all transient, because the thing that we haven't showed you, but is a part of this, is that everything's in motion. So not only is it 3-dimensional, but it's actually much more than that, because everything in this, what we're flying you through, is moving. And so the sun right now is closest to Proxima Centauri, Alpha Centauri at 4 light years. But get ready, because in 1 million years, there's a star called Gliese 710, and it's coming towards us, and we're coming towards it. And it looks like that thing is only going to be about 16,000 times the distance between the Earth and the sun in roughly 1 million years. So get ready, start looking at that star and paying attention, because if it's got a solar system, we've got our solar system, we're going to have what Carter liked to say, dancing Kuiper belts, dancing Oort clouds.
I can show that. Maybe that's a nice thing to sort of end on. I'm going to turn the star labels off.
Yep, right. And we're taking you back to Earth, and we're gonna wrap up here.
Another thing, I feel that we ought to emphasize is just how dim our sun is. It's the central star. We can see Sirius and Procyon on the right, and Alpha Centauri on the left. But by understanding stars, we eventually understood that the sun was a star too, and that it's a dim star. And what it lacks in brightness, we have to thank for its longevity, and that it's been around for about 5 billion years. The oldest Earth rocks are about 4.5, and the oldest, and the moon rocks too. We learned that the moon and the Earth are sort of perhaps shared a common origin from a large collision. So by studying science and looking in detail at things, we really begin to piece together what we've just shown you. By this act that started out in mapping just by this almost like grid work you see in the sky. That's what astronomers use. Think of it as like graph paper in the sky. And if you have graph paper in the sky, you can measure where a star is and say, oh, it's 3.5 from this and 5.5 from that. And so that process is what we put together in this digital universe to show you this map.
So we want to thank you guys for joining us. 2 reminders. Number 1 is that there's going to be a survey that's going to show up at the end in the chat. We'd love for you to fill it out so you can give us some feedback on, we'll be live here for a bit longer, so you can get this chat with the survey here, so we can get your feedback on the program, what works, what doesn't. And also, as a reminder, we do these Friday live chats. We'll be live again here next week at 1 p.m. We'd love to have you come back and join us to keep exploring different aspects of STEM. Next week's going to be on bats. And so come back for some bat knowledge next week.
Same bat channel. Great. So I guess that's it. I want to thank you all once again, and my own fascination with astronomy started when I was about 10 years old and encountered a map in the library of the old Hayden Planetarium, a map that showed us how vast the universe was and all the little galaxies you could see just by looking closer and closer. So thank you all for joining us. Thank you, Jackie. It's been wonderful. And keep enjoying the universe. Bye-bye.